You watching? Not exactly. Okay, look up here. I'm going to teach you how to interpret graphs of the, well, basically of the titration curves. We call it the titration curve. It's the pH versus the volume. And yours looks kind of like this, but not exactly. There's a lot of questions I could ask you about this. This is what a titration curve would have looked like last year when we did a strong acid and a strong base. Notice the pH at the equivalence point was 7. It's a very sharply defined equivalence point. And before and after look pretty much the same. All right, that's not what yours looks like. Is your jump, is the pH at 7 there? No, it's not. Hold on, you can't come in. I'm taking it. All right, so, all right. So basically, this is what a strong acid and a strong base look like. All right, that's not what you did. Okay, so we got to show you what yours looks like. But the point of graphs, as always, remember these graphs? He's never coming back. The point of any graph is the point of any graph is to make life easier. Okay, you got. I can't let that. You want to make life easier. And these, if you remember, when we did the rate law expression graphs, we did not first time do it like this. The first lab we did trial 1, trial 2, trial 3. It took like 3 periods. All right. This one, we only did one time, and we graphed it 3 different ways, and we were able to tell, if you remember, the concentration versus time. If that was your representative graph, if that was a straight line, it was what order? Do you remember? No, it was not first, and that's a good mistake. It's 0 order because concentration versus time, it had no effect. It didn't slow down at all. All right. Whereas even despite the fact that your concentration was changing, this guy here first order, this guy here was second order. But my point is, these graphs also tell you stuff, and I'm going to ask you multiple questions on the worksheet I'm going to give you for tomorrow, and some of those questions are asked on this lab you're finishing right now. So you can't answer these questions. After I'm done, I'm not going to help, especially Dylan. I'm not going to help you because you should be listening to this now, and you'll know how to answer all these questions. Okay. So, some of the questions I could ask you. I could ask you, what is this a graph of? Is this a graph of, am I adding an acid to a base or a base to an acid? What do you think? I'm adding a base to an acid, you all agree? Because the pH starts low and ends up high. I can ask you, is this a strong acid titrated with a strong base? Or is it a weak acid, weak base, weak acid, strong base, weak acid? I could ask all those ways. What is this one, you think? Strong and strong, and I'm adding the base to the acid. So that's how you put it. Strong base added to weak acid. What about, now look at the difference between that and this. That's the other extreme. This is a weak acid added to a weak base. There's like no endpoint. Okay, there's like no sharply defined endpoint because you have a buffered solution. You have a buffered solution when you have your acid and its own salt there. So things change just gradually. You really can't do, no one's ever going to ask you to do a weak acid, weak base titration because to find the endpoint is almost impossible. All right, very, very difficult anyway because it's so those are your two extremes. Let's look at what the other things look like in between, right? And the kind of questions this is our graph. This is the one you got, right? It's exactly what we did, but there's some things you need to know. First off, I want you to mark right now, because you have it all graphed. Mark the equivalence point. The equivalence point will be where that halfway up where that big jump occurred. Now look at it doesn't mean halfway up necessarily the exact point where you took the pH. Try to look at taking about halfway up the big jump and mark it. You'll notice it will be in the basic range, isn't it? Make a big mark there and call it the equivalence point on your graph. Okay? Now the region before that, look here. This area here you want to mark also on your graph. This area here is the buffered region. And I could ask you, which part's buffered? This is buffered. And you know it's buffered because you were dumping base in there. And it was barely changing its pH. You just saw that in the lab, right? You were dumping pH in there and nothing happened. You might say to yourself, well, this is buffered too. Is it? Yeah, this is just base. You don't have to write this down. You don't have to write anything up here. The point is this is not buffered. The reason this guy's not changing much is because you've used up all the acid, and all you're doing is you're adding base a slightly more concentrated strong base, to water, which is diluting it a little bit, and it's getting a little bit more basic as it goes on. But that's not it by no means is a buffered solution. A buffered solution has to be able to resist changes both ways, and this is the buffered solution because you have both the salt of the weak acid and the weak acid himself. Okay, I'm going to come back to this guy at the very end because that is how we're going to do our last calculation. We're going to do a calculation where we can find, and I'm going to explain why the pH and the pKa are related at the half equivalence point in a little bit. But first, I need to show you some other graphs, some other ways they can look. What do you think that would be? I need you to answer two questions first. Is it a strong acid, strong base, weak acid, whatever that is, and who's being added to what? Okay, let's see. The endpoint is basic. The endpoint is basic, correct? You see it? Halfway up is in the basic range, around 8 point something. So if the endpoint is basic, what do you think you probably have? What are two things you have? Strong base and a weak acid. Okay, now who was added to what? Yeah, the weak acid was added to the strong base. In other words, it is, if we did our lab, in reverse. If we did our lab by taking the base in the jar and we added the acid, the weak acid to it, it would look like that. Okay? All right? Now, let's look at some other possibilities. What is this guy again? Strong base added to strong acid. Okay? Okay, this is big. pH is 7. That's the giveaway right there. Anything buffered in this? Either region buffered? You cannot have a buffer solution if you have a strong acid and a strong base. We just saw that one. Let's look at this one. What do you think that is? It's a strong. No, they're both strong. The pH is right at 7 at the halfway point. But who's added to what? Acid added to base. Strong acid added to strong base. See it? Everybody getting these? How about this one? Weak base, strong acid. Weak base is being added to a strong acid? No. No. Say it again. Yes, you did. That's what I heard. Weak base added to strong acid. I heard that. Somebody said it. All right. So, first of all, let's decide what the two things are. The pH at the end point is slightly acidic, right? So that means it's going to be a strong acid and it's going to be a weak base, right? But who was added to what? The acid was added to the base, right? Okay. And now, this one over here, what do you think?
Strong base, weak acid added to strong base.
Weak acid added to the strong base. You've got to say them in the right order of what I want you when I'm asking you that. Do we have buffers? You should also be able to tell the buffer solutions. If you've got a strong, there's no buffer. Okay? The weak one, it's going to be buffered on the side where you have both the strong, weak acid and his salt, or the weak base and his salt. Okay. Now, last thing I want to say before I get to the calculations you got to do for the lab is this. The point, these kind of graphs, and I actually saw one of the questions in a multiple choice question for the AP exam, was what indicator would you use? Okay? If it tells you you've got the choice between using phenolphthalein or methyl orange. Phenolphthalein turns, remember, we used Congo red the other day. Remember I told you Congo red changed around 4 to 6, 7, between 4 and 7? Okay? You have to decide which indicator would you want to use. If you've got a graph that looks like this, I could use phenolphthalein, but I couldn't use methyl orange, right? It would not. It has to. The color has to change at the end point, or you won't know it. So the key to that one is the key to those kind of questions is choose the indicator whose pH changes where this guy changes, and you'll be able to tell that by deciding, okay, well, he's going to change in the acidic range. All right, if you've got a strong acid and a weak base. So I would need to use methyl orange. Phenolphthalein turns us slightly in the basic range, so it would be the opposite. I would want to have something with a strong base and a weak acid. Okay? So that's why we use phenolphthalein, by the way, for our lab. If we had used methyl orange, we could not have gotten an answer. It wouldn't have turned when it was supposed to. All right? Okay. Now, time for the calculations. The rest of the calculations you have to do on your paper. Okay? Oh, I almost forgot. One last thing. What if I got a graph like that? This is also in your lab and in the worksheets. What if I got a graph like that? What does that tell you? Kind of hinted at this the other day. I talked about it with normality instead of molarity, because why do we worry about normality? If there's more than one hydrogen or more than one hydroxide. Yeah. So what's happening here? I'm adding, first of all, am I adding an acid to a base? I'm adding the base to the acid, correct?
Yeah.
All right. It must be a weak acid, all right? And because the pH doesn't change right at 7, but it's got 2 places where the endpoint happens. You know what that probably means this guy's formula was? What do you think? What do you think? How about, come on, H2A? You see, because I told you the other day, you have to be careful. These guys have, they're going to break up in different steps. So if this guy breaks up and gives off, well, say you're adding water to him, okay? And he's going to lose 1 H. You'll still have the HA plus hydronium ions, okay? But then that HA can break up in another step, and that's exactly what's happening here. You've got it happening twice, all right? Both of those are the equivalence points for the first H leaving and for the second H leaving. So this would be a diprotic acid. What if I have one that looked like this? What do you think that's going to be? Let's see, 1, 2, 3, right? Triprotic, right? Triprotic acid. And each one of those equivalence points is corresponding to one of those H's breaking off, and they all have their own Ka. Each one of them has their own Ka. All right. Now, speaking of Kas, I got to teach you about this half equivalence point. If you remember, and I think you probably do, when we were doing the Henderson-Hasselbalch equation, remember this? pH equals pKa plus the log of the salt over the acid. All right? And I hinted at this. I said, what would happen? I guess I kind of do some of these in my head. But there's one special one I could do in my head. Real easy. If the concentration of the salt and the concentration of the acid, whatever it is the same, then I have a 1. What's the log of 1? To what power does 10 have to be raised to give you 1? 0. So all you're adding is 0 to the pKa. Guess what that means? At this point, right here, because at the half equivalence point, the concentration of salt and acid is exactly the same. At that point, the pH is the pKa. I don't have to even do a calculation. I can just look at my graph, whatever that pH is, I know that's also the pKa. And so if I wanted the Ka, all I'd have to do is take the inverse log of the negative pH, because it'd be the same as the inverse log of the negative pKa. You understand? And that's one of the things you got to do in your lab in a minute. You're going to have to do that in just a few minutes. If you look at the sheet here, let's see. Right now, let's just go through the problems. You've already graphed it. All right. You've already marked the equivalence point. I hope most of you marked the equivalence point, right?
Yes.
Halfway up that jump. Now you want to mark the half equivalence point. The point halfway between here and the beginning of your lab. Mark that half equivalence point. And that will be on here. Right about there. Halfway between the big jump, where you have the big star for the equivalence point. And you can tell that because that star is going to be on, like, say it's on 13. You just take half of 13, right? And then wherever that shows up here. Okay? And by the way, this is the same graph you guys made. It even looks just like it. Even has the same numbers, pretty much, that you guys have. Now, here's my point of all this. Let's see where we are now in the calculations. You're actually looking at calculation number 5 here. Okay? If you just mark this at your paper right now, if you draw your line over and you see what the pH is, what is it around? 4 point something? Yeah. Right? Most people it's 4 point something, right? Take the inverse log of the negative 4 point something for the pH. You know what you're going to get? Do it. You're going to get the Ka of acetic acid. And you can look him up in the back of the book, and you'll find that your answers are pretty darn close to the correct Ka. What'd you get? Did you do it? Yeah, inverse log of the negative pH at that point. What'd you anybody get? Inverse log of the negative pH. Okay, what else? Anyone else get some of theirs? 1 point what? 2.8. Okay, times 10. And then all of these are times 10 to the negative fifth. Is that correct? We're going to put them all on the board. I'm going to stop recording now because they're basically done. But we're going to put them all on the board, and we'll take the average. And I bet you we come pretty close to the correct answer. Yeah, we don't need that. Okay.